So if you're looking for delta, you want to resolve this. Okay? So just delta, you have force times the length over cross-sectional area times modulus. So this is become a standard equation. If you are looking for deformation or elongation because it's stretch, it will be force times the length of the pipe over here cross-sectional area of the pipe times the modulus of elasticity of the material. So this modulus of elasticity. So that become an equation. So this is a formula. If you are looking for how much this is area has been stretched, then you know the force times the length over the cross-sectional area of the pipe times the modulus of elasticity. Modulus of elasticity is given in the table. For each material, there is a value for the modulus of elasticity. Any questions so far? Okay, let's see, we have a problem here. We have a beam column and we have a force internally, the force here, and also the force at the end of the column is 120 Newton. You may imagine the column, this is a nose landing gear strap. So the force that come through here the force that there's a force, the link here give a force here, and the force here will resolve. That's why you have a component force. Okay, and you have a force here, attachment with another component force here, and the wheel itself also giving you the force. This is just an example. This example the problem. Okay, the example problem here, if we have this nose landing gear, okay, you may have a question how to calculate the stretch of the nose landing gear strap in flight when landing gear extended before landing. So you can calculate using the you can calculate using this one. Okay. You can calculate using the equation that we have here. Okay, remember we have here, we can calculate using this theta equal P force length over area times the modulus. You can calculate the stretch, how much landing gear has been stretched. Questions?
No, sir.
Okay, let's try to work out here. This is a column. The cross-sectional area of area A is 551 millimeter square, and this area for the CD, that 581 millimeter square is for the whole A, B, C, D, for the whole column, the whole cylinder, and the area CD is 194 millimeter square. We have point force here 300 kilonewton. We have 150 newtons and 120 newtons upward. So you may look at this as a landing gear for you to appreciate what we're trying to do. Okay. And imagine we have a wheel here. So we have force here. We have a force going up. And we have the force coming down because the weight of the wheels. So we have 300 Newton kilonewton. Okay, where do you get the force? Because we have, remember, we have a strut. We have the strut here acting on this. The strut give you the force. The force acting downward is 300 kilonewton. And we have reacted force going up here. Due to the joint, we have like 150 kilonewton. It's just trying to visualize. Then the whole wheel assembly is 120 kilonewton. 20 kilonewton. So all the forces are acting. Now, the question is, determine the deformations, okay, of this section under these forces. So what do you do? First, okay, this is standard way to do it. First, you divide the rod into components. At load application point, apply free body diagram, and evaluate the total component deflection. So 3 areas, 3 things. One, 2, 3 steps. Divide rod into component, apply free body diagram, then evaluate the total. So here, what do? We make a section. Yeah? We make a section and we make a free body diagram. Okay. First section, we have the whole diagram. Okay. We have here, and we have forces here, and we have the total force. So here we have 300, and here we have 150, and the force here is 120. Now we make into section. Remember we say apply free body diagram. Divide rod into components. So we have first component. We cut. We cut here. And then we have a component breakout. So we have here is 120. 120 kilonewton. What will be the P3? Say we can say here is P3. So the reaction is say here is P3. So this is the starting of the free body diagram. So P3 will be 120. So P3 will be, this is 120, so P3 will be 120. Now we make another cut. We make another cut. We have one whole section and we have cut somewhere there. Okay. Now we have 120. 1 kilonewton, and we have 180. Sorry, this is 180. This one is 8. Sorry, my mistake. 180. Okay. So here we have 180 acting. We know already, we put it back here, 180. 180 kilonewton. And then we have P2. So here is P2. Then you make a equilibrium equation. P2 minus 180 plus 120 equal to 0. So P2 will be minus 60. Okay. Now you have another equation. Let me cut this one off. And we have another equation. We have to develop another equation. We have not solved it yet. P2. This is P2. So the P2 we cut here. Remember, add load. Okay. Component add load application point. So load application point 150, 180, cut here. So another load application point here, 300. So you have another cut here. Okay. So we another cut here. And here is 120. And here is 180. And we have 300 going in that direction. 120 kilonewton. We have 180 kilonewton. We have 300. And then what is a P3? P1. So we may say this is P1. So what is this P1? So you have to develop the equation, another equation. So it will be P1, okay, plus 300, okay, minus, because going to the left, and minus 80, plus 120 equal 0. So minus P1 plus 120 plus 120 equal to 0. You have minus P1 equal to 240. P1 is minus 240 kilo Newton. Okay. So we have 240. So you got all the load point here. You have the forces inside here. You already have forces given here. You have forces inside here. You have the forces inside here. So all these forces will be used to solve the problem earlier, which is the deformation is force time L cross-sectional area time modulus. I can use this equation. So you can sum up. That's why you can say sum up, which is the summation. Okay, summation of P1 L1 A1 E is constant. So far, any questions? So now we may say that we try to solve this problem with area. How long is that the whole structure for nose gear will be extended? So this is the question, this is the answer. So you have P1, P2, you do it one by one. Okay, you can bring the E is constant out, equal modulus is out. You multiply by P1 L1 over the area. Okay. So delta will be 1 over modulus. P1 is what? P1 is 240. Okay. 240. L1 is 300 millimeter. That's given. L1 is 300 millimeter. 300 is, you should divide by 300 to the 1000. You want to have the units meter over. Okay, this one P1 L1. A1 is 580 millimeter. So 580 millimeter. You have to convert into meter square. And then you continue doing that. You can see here. So here is P1, which is from here to 40. The P2 is here. And P3 we plug in here. And L1 is 300, L2 is 400. So L1 here is 300, L2 is 300, L3 is 400. So you put L1 here as this one is 300, L2 is also 300, and L4 is 400. And then the deformation, if you solve them all, you get 1.73 millimeter.